Question 11 says the capacitor shown in the circuit diagram is initially uncharged. Switch S is closed at t equal to 0. Value of time t at which charge on the capacitor becomes 250 microcoulomb is. So we have to find the time at which charge on the capacitor becomes 250 microcoulomb. Let's look at the expression for the charge on the capacitor as a function of time. So first of all, what we do is we look at the final potential difference across the capacitor when the circuit in fact achieves a steady state. So we can see that in that case the current in the capacitor will be 0, and which means 30 volt potential difference is divided between the 3000 ohm resistance and the 6000 ohm resistance. So in fact this potential difference, if I call this point A and this point B, in steady state VA minus VB becomes a 6000 divided by 9000 into 30. So this simplifies to 6 by 9 into 30 volt, and well, this in fact will be equal to 20 volt. So that is the final potential difference across the capacitor. Initially of course it is 0 just after closing of switch. So the final charge on the capacitor, let's call it QF, is in fact 50 microfarad. That means 50 into 10 to the power minus 6 coulomb multiplied by 20 volt. So this in fact will be in microcoulomb, and we see that this is coming out to be 1000 microcoulomb. This is the final charge on the capacitor. The expression for charge on the capacitor as a function of time t is in fact 1000 microcoulomb into 1 minus e to the power minus t divided by tau. So we shall of course find the value of tau, the time constant. To find the time constant, we consider that the battery is shorted, the switch is closed, and in that case what is the effective resistance between these 2 points? Let's call these 2 points as small a and small b. Well, we find that this 3000 ohm and the 6000 ohm in that case will be effectively in parallel, and 3000 ohm and 6000 in parallel effectively give us 2000 ohm. So the effective resistance for finding the time constant we can take as 2000 ohm. So the value of time constant tau is 2000 into C, that means 2000 into 50, and this will be in microsecond. So this is in microsecond. Let's simplify this still further. This we find is in fact coming out to be 0.1 second. Considering that 1 microsecond is 10 to the power minus 6 second, the time constant is 0.1 second. Now the value of Q has to become 250 microcoulomb. So the equation now is that 250 is equal to 1000 into 1 minus e to the power minus t by 0.1 second. And let's simplify this still further. We have 1 by 4 equals 1 minus, so this we get as 1 by 4 equals 1 minus e to the power minus t divided by 0.1, or let it be 0.1 here. So that means we have 3 by 4 is equal to e to the power minus t divided by 0.1. Further, what we get is, if we take log on both sides, ln 4 by 3 then would be equal to t by 0.1, and that means the value of t is 0.1 ln 4 by 3 seconds. So this is 0.1 ln 4 divided by 3 seconds. So the question is solved. The value of t we find is coming out to be 0.1 ln 4 by 3 seconds, and that in fact is matching with option 4. So option 4 is correct. Let's go to the question number 12 now. Question 12 says the resistance of a resistor with color code as shown in the figure is, and the color codes are orange, yellow, black, gold, and the 4 options are given. Of course, question is based on the concept of color coding of resistors from the chapter current electricity. Now, to be able to calculate the value, we of course need to remember, well, the sequence. The sequence is BBROY, we call it BB Roy to remember easily, and then it's GB, Great Britain. So this is BB Roy, Great Britain, and then there is VGW. So this is the sequence, and of course we need to know what is the number associated with each one. This one is black and the number here is 0. This one is blue, here it is 1. For red it is 2, and for orange it is 3. For yellow it is 4, and the fourth one, the gold, is for tolerance of 5%. So well, this is enough. Some other color had been there, we would have gone further in the sequence. Right now it's not required. Now as far as this resistance is concerned, well, the first two bands in fact give us the two significant figures as far as the resistance is concerned, and in our case we have orange for 3 and yellow 4. So that means the first two digits are 34. The first two significant figures are 34, and the multiplier, well, we see that it is black and 10 to the power 0. The multiplier is 1, so this is 34 into 1. That is in ohm, and of course plus minus of, for gold it is 5%. So this is 34 ohm plus minus 5%, and that means option 2 is correct for question 12. Let's now go to the next question. Question 13 says an LC circuit contains a 40 millihenry inductor and a 25 microfarad capacitor with an initial charge of 20 microcoulomb. The switch is closed at time t equal to 0. If the circuit has negligible resistance, then the minimum time at which charge on the capacitor becomes 10 microcoulomb is nearly, and the four options are given. Well, the question is from the topic AC circuits and based on LC oscillations. Let's say this is the situation. We have the capacitor and the inductor connected like this. Now initially the current is 0 and the charge is 20 microcoulomb on the capacitor. So on this, here there is plus 20 microcoulomb, there is minus 20 microcoulomb, and this is the situation at t equal to 0. Now if we consider that current will in fact start flowing like this, so we can see that the initially charge on the capacitor starts decreasing. So we have initial charge as 20 microcoulomb, the initial current as 0, and we also note that as switch is closed, the charge on the capacitor starts decreasing. Well, considering all these facts, we can write the expression for charge on the capacitor as a function of time. Qt is equal to initial charge, which in fact is 20 microcoulomb. Let's say 20 microcoulomb into cos of omega t. So it satisfies everything that we have talked about. At t equal to 0, charge is 20 microcoulomb, and charge on the capacitor, well, initially starts decreasing. So the slope of this term for t just greater than 0 will in fact be positive, and at time t equal to 0, of course, current would be 0. So with all that, this is the equation. The value of omega, of course, is 1 by under root of LC, the angular frequency. Let's calculate the value of 1 by root LC. Well, this is then coming out to be under root of L into C. The value of L is 40 into 10 to the power minus 3, and C is 25 into 10 to the power minus 6. So that means we have in the denominator a factor of 10 to the power minus 92. So this is the angular frequency in SI units. Let's simplify the value of omega once again. So the value of omega, we see that is coming out to be, we have it as, well, 1 by 1000 into 10 to the power minus 9, and there is square root, of course. So this is, let's say 100 into 10 to the power minus 8, and this will be second inverse or radian per second. This is further than, this in fact will be 10 to the power 4 divided by 10, or simply 1000 radian per second. So let's say this is radian per second. That is the value of omega. Now we have to have the charge on the capacitor has to become 10 microcoulomb in the shortest possible time. So that means from this equation we put Q equal to 10 microcoulomb, and the cos omega t then becomes 1 by 2, and that means the smallest value of time we can take such that omega t is in fact pi by 3, and the value of t would be pi by 3 into omega. So this then is, we now need to put the value of pi as well as the value of omega that we have found, and this is then 3.14 for pi divided by 3 into 10 to the power minus 3, because the omega is in the denominator, and of course this is in seconds. On simplification, this is then coming out to be 1.05 millisecond, and that means option 1 is correct for question 13. Let's now go to the next question. Question 14 says a uniform string of length L is suspended from a fixed support. A short wave pulse is introduced at its upper end which starts moving down the string. The time taken to reach the center of the string is, and the 4 options are given. So clearly the question is from the topic waves, and here we are talking about transverse waves in a string. Let's say the situation is something like this. This is the support and this is the string, and the string has length L. Now let's consider a point at distance x from the top. So we need to find the speed at this point. Let's call it point P, and to know the speed, well, the formula for speed in fact is under root of tension by mu, but the value of tension is, this tension is due to the weight of length L minus x, and that is this length. The tension in fact will be mass per unit length mu into L minus x multiplied by g, that is t as a function of x. So the velocity which we can say is dx by dt is then coming out to be under root of mu into L minus xg by mu, and that means it is L minus x into g. So to find the time, we have the differential equation now. This is under root of L minus x, and on the right hand side is root g dt. So we can now integrate. The value of x is going from 0 to L by 2, whereas the value of t is going from 0 to t. And let's integrate. The left hand side will give us in fact, it is L minus x to the power minus 1 by 2, so this becomes then plus 1 by 2 divided by minus 1, so we have minus 1 coming here, and the limits would be, and of course we need to divide it by 1 by 2, that means there is a factor of 2 also in the numerator. So we have integrated dx by under root L minus x. We now need to put the limits. The limits of x are 0 to L by 2, and on the right hand side is root g into t. So let's now put the limits. We get t is equal to 1 by root g. There is a factor of 2 also in the numerator, and if we put x equal to L by 2, so we get it as minus root L by 2, so minus root L by 2, and the next term will be when we put x equal to 0 as root L. So let's simplify this still further. This will then be equal to 2 root L by g into 1 minus 1 by root 2. On simplification and rearranging, that's the value of t we are getting. And that means among the options, option 3 is correct. It is matching with what we have got. Time now to go to the next question. Question 15 says a body floats in water with fraction F1 of its volume outside water. When the same body floats in an oil, fraction F2 of its volume remains outside oil. The relative density of oil is. Clearly the question is from the topic fluids, and it's based on the Archimedes principle. When the body floats, the weight of the liquid displaced in fact is equal to weight of the body. So that means weight of the body, if we assume, is W, we have weight W is in fact equal to its total volume V, and since only fraction F1 is outside, so that means what is inside water is 1 minus F1 fraction. So this is the volume of water displaced. This multiplied by density of water into G is W. and when it's in the oil, well, the fraction of volume inside oil will be 1 minus F2. So this is in fact the volume of oil displaced. This we have to multiply it by density of oil into G. So that is the weight. Now from this equation we can easily find the relative density. Relative density after all is density of oil divided by density of water, and we can see that this is coming out to be 1 minus F1 divided by 1 minus F2, and this in fact is matching with option 1. So question 15 is done. Let's now go to the next question.